Hello everyone, this is Puya. Um, just I'm just going to describe what you'll be doing in the lab 0, which is a basic introduction to Simulink. In this lab, we are going to be working with a built-in example from MATLAB and modify it according to the video that you just watched. So the built-in example that I want you to simulate is this one, power underscore PWM generator 2 level. So if you click enter, then you would have this Simulink model open. So let me just extend the window. So first of all, one thing I wanted to mention is that if you want to make your screen fit to window, you can click on this one so that you don't miss anything that might be somewhere in the corner over here or over here. So now we see the full model. This is an example of a 3-phase inverter that inverts the DC voltage into AC. There is a filter here and there's a load here, and here you would see that you measure voltage of phase A with respect to 0, voltage of phase B with respect to 0. You subtract them to get the voltage of line-to-line voltage AB, and then using the RMS block, it shows the RMS value here. You also have two scopes here that shows voltage of phase A and voltage line-to-line voltage AB, and also shows the line-to-line voltage of A minus voltage of phase B at the load after the filter. Okay, the choke is basically an RL filter here. So also at this point you have the PWM generation, so you don't have to make it yourself. You can actually make it yourself if you want by generating a sinusoidal waveform and subtracting it from triangular waveform, but this one is made for us. So here you have a sinusoidal waveform that's multiplied by something called modulation index, which is just basically is gonna reduce the amplitude of this sinusoidal waveform to 0.95% of what it used to be. And then over here, the sinusoidal waveform is compared with a triangular waveform that's its frequency is 30 times more than the sinusoidal waveform, right? So it's more frequent than the sinusoidal waveform, excuse me, and this would generate a PWM signal, and a square wave signal which its pulse width is going to be variable. And then over here you have some transistors and some diodes that based on this PWM signal would convert this DC voltage to PWM AC voltage, okay, which its pulse width is variable. Now here we have 3 phases. So the 3-phase inverter which you have here would have 6 transistors and 6 diodes, so 6 of these, and would have 3 legs. What I want you to do in this lab is basically convert this example into a single phase inverter. So there are many changes that we have to make. So first of all, here we have an RL circuit, which is in series with our inverter output and load. It's placed between them. So first of all, we have to change this to a single phase RLC circuit or RL circuit. and this is a three-phase load, we have to change it to a single phase load. So, and also the same thing here, this is a three-phase inverter, we have to make it a single phase inverter. So let's start with that. So first of all, one thing I showed you before and I want to emphasize on it before, this is probably the most important um, button or tab that you have to work with. This is the library browser. Everything, every elements that you want to place on your Simulink model, it's going to be here. So you can open this, and here I want to have an RLC circuit instead of this one, right? A single phase RL or RLC filter. So I would just type RLC and press enter. So excuse me. So if you see here, I have an RLC load and RLC branch. This is a branch, this is not a load. So I would just drag and drop this one here. And I also have an RLC or RC load here. So I again go to library, and this one is in parallel. So I'll find the parallel RLC load wherever it is. Did I miss it? Parallel RLC load. So this one. So I drag and oops, cancel, drag and drop. Oh my god. Drag and drop it here. Okay. So let's look at this one, this three-phase filter. Let's double click on it. You see that its resistance is 1 milliohm and its inductance is 400 microhenry, and it doesn't have any capacitance. So what I do here, I basically do the same thing. Resistance 1 milliohm, inductance 400 microhenry, and capacitance was 0. So this basically smooths the current, right? Which also like reduces the voltage ripple as well, like on the outside, on the output of the filter. So again, like let's double check this. Yeah. So I'm done with this. I can delete this one. I don't need this anymore. Let's look at the load that we have here. The load, usually we characterize the load with its active power and reactive power. So here the active power that this load consumes or absorbs is 500 kilowatt, and its reactive capacitive power, it's 100 kilowatt as well. So reactive and inductive, its inductive one is 0. Okay, so this is basically a type of load that would consume negative reactive power. It basically generates reactive power. Okay, so let's just again, but this is three-phase. So what I do is maybe to be more realistic, well, I keep it the same. Let's just assume that it's a big load, 500 kilowatt and 100 capacitive, and let's keep its inductive reactive power equal to 0. One thing I wanted to show you here is that you saw that the voltage RMS is 600, but this is three-phase. So let's make it let's divide it by square root of 3 to convert to single phase. If I do that, 600 divided by square root of 3, let's just see what that is. 600 divided by square root of 3, it's almost 346. Let's just put 350 or 348. Doesn't matter. Something like 350 or 346 or 348, doesn't matter. Okay, again, I'm done with this one, so I can delete this one as well. Now, the other part that I have to change is this one. So as I mentioned, for three-phase inverter, we need to have 3 legs or 3 arms. But for a single phase, you either need 1 or 2. Okay, so let's first do 1 arm. We don't need to make any changes here. These are the loss information and the protection information for the transistors and the diodes. So that was the only change we had to make. And as you see, as we did that, the B and C are gone in this case. Okay, so this is what we have right now. I'm gonna double click on the UREF generation as well. So here, maybe because we're in North America, make this 1 pi times 60 hertz. And okay, so this setting for phase is for 3 phase. You know that phase A, phase B, and phase C, they are 120 degrees apart. So if you only have single phase, then you only need this one. So basically this shows that our reference sinusoidal waveform has 0 reference. The sample time, I'm going to talk about it later. 0.95 is multiplied by this one. It goes here. So let's double click on this one. 32, again, this is the triangular or the carrier frequency. It's 30 times the UREF frequency. So I'm going to make this 33 times 60. And again, here it says that 3-phase bridge, 6 pulses. But we want to go with single phase. And because we chose only 1 arm in the inverter, that means that we are running a half-wave bridge. Or sorry, half bridge or half-wave inverter. So you have to make that change here. Okay, so now this is okay, this is okay. Now what I need to do, I'm just going to delete this one. What I need to do is, just going to make it look nicer. I need to place the filter here. So you can just connect it. Oops, it's not connected. Yeah, it is connected now. And I'm gonna delete these lines that I don't need anymore. This is our load. Okay, can you guys tell me where this end is supposed to go? It's supposed to go to ground, right? So it's supposed to go to neutral. So I'm gonna go to, either can copy this one and paste it here, but I wanna show you that we can find it from the library. So I'm gonna go and write neutral. Enter. Okay, so one thing I wanted to tell you is that you installed MATLAB and Simulink with some toolboxes. One of the toolboxes we installed is Simscape. Simscape has some elements that you can see here. This is like Simscape. These are the elements from Simscape. These ones, and as you can see, they're like in blue or green color. These ones are not compatible with original Simulink blocks. So if I try to get this neutral, it's not gonna attach here. So what I go down and I find this neutral, it's in black. I drag and drop it here. I connect it, it gets connected. So everything looks okay so far. Now, what I want to do, I want to see the impact of this filter on the voltage. So I'm measuring the voltage here before. Okay, I don't need this one because we don't have two phases anymore, so we don't need to delete them. Sorry, we don't need to subtract them. What the hell is this one doing here? Okay, so excuse me, sorry for my language. And also want to measure the voltage after this filter. Okay, so I want to connect this one to here. Let's make it look nicer. So I right click on it and I go to rotate and flip, block. I flip it upside down, okay? And I connect this one to this scope. So I have one scope that's showing the, and I don't need these formulas anymore, so I'm gonna delete them. And this is not VAB anymore, so like this is V of converter. So I just clicked on it and I say like V converter and I say like V filter or filtered. Enter. Okay. So I'm measuring this voltage and this voltage. Let's also measure the or see what the PWM signal look like. Okay, so this is a scope. It basically simulates an oscilloscope. So let's actually go here. And again, I'm gonna search for a scope. It's found here. So I'm gonna drag and drop it. I can make it green like this one, but doesn't matter. So I'm just gonna connect this one to here. Okay. So we are good and we don't need this one anymore. I'm gonna delete this. I'm gonna connect this one here. This is gonna measure our filtered output voltage, and it's gonna show how this is gonna change. Okay, so this one shows the runtime. So it means that Simulink, once we run this model, it's gonna simulate this circuit for 0.1 seconds. Okay, so let me run this first. See if it runs. Seems that it ran. I also like don't need this one. I'm just gonna delete the text. This is not, I'm gonna move this a little bit up so that I can zoom this. I can zoom this now, fit to window. Now it seemed that it ran, so let's see what our voltage of the inverter look like. Okay, so if I see this, you see like this is, well, it looks fine, but it's too much, right? I don't need to run it up to 0.1 seconds. Maybe I can just go to 0.02 seconds. So what I'm gonna do, I'm just gonna change the runtime to 0.02 to make things more visible and make the resolution better. Can make also this one 33 times 60. So that adds 330 to this one. that would be 1980. Doesn't matter, this is text, it's not going to be compiled, but let's run this again. Okay, so now this looks much better, right? So I can actually see that this is similar to a sine wave, right? So this is how we model a sine wave using PWM signal. You see here the width of the pulse is basically increasing up to here and then decreasing, and then it goes to negative part, increasing, decreasing, and then it continues, right? If you find the frequency of this one, it should be again 60 hertz. So after 60 hertz, it repeats itself, right? So it's around like 15 milliseconds. So this should be around here, or 16 milliseconds should be around here, that this signal repeats itself. And let's see like what this RLC circuit or RL circuit that we have here did to our voltage. So let's see the voltage of the filter. Oh wow, it looks much nicer, right? So it actually looks sinusoidal, right? So this is what the filter did for us. It basically removed all the high frequency harmonics, right? Let's look at our PWM. Okay, so this is PWM. Now this one, if you look closely, you see that we see blue and yellow. Okay, so single phase bridge, if it's half wave or like half bridge, it would have two switches, right? So we need to have two gate signals. So that's what we see here. We see two gate signals on top of each other, but they're not very clear if I display them like this. So what I do, I close this one. So what I know here is that this generates two signals. So like I'm showing two signals here. I want to separate them. So again, I go to the library. There is something called multiplexer, or short MUX, and demultiplexer. Okay, so demultiplexer is what I need. I need to separate two signals into two separate signals. So I'm just gonna again drag and drop this. I'm gonna connect this one here. I'm gonna move this one here. Okay, so now I need to change the number of inputs that this scope takes. I have to right click on it. Over here it says signal and ports, number of inputs. It's 1. I want to change it to 2. Now this one was added, so I'm gonna connect this one here. Okay, now if I double click on this, it shows the same thing that we had before, because we ran it before the changes. So I have to run it one more time. Okay, now if I look at it again, I see the same thing. So if you guys go here and click on layout, okay, it shows that you can separate the windows into two separate windows now. Perfect. So now I see the PWM signal for two switches, and as you can see, they're complementary. Once this is 1, this one is 0. Once this is 0, this one is 1. Okay, the 4420 students, they realize like why this is the case. The 3130 students, for now, just like work with Simulink. You see why this is the case later on in your future course. Okay, so we converted this three-phase inverter to a three-phase inverter to a single-phase inverter. We measured the voltage before the filter, voltage after the filter. I also want to measure the current. So I'm going to go here and I'm going to write current measurement. Okay, I find the current measurement. I drag and drop. Maybe I need one more, so I'm going to drag and drop one more. So you remember that when you want to measure voltage, you have to connect them in parallel. So here we're measuring this voltage with respect to 0. Here we measure this voltage with respect to 0 again. But for the current, if I want to measure the current before and after the filter, I have to put it in series. So I have to put it here. Okay, so I have to put, I'm going to delete this one. I have to connect this one here. And then this one goes to here. I have another, so let me move this one here. I want to also like place another amp meter after the filter. Plus goes here, negative goes here. Let me bring this down. Let me actually bring the whole thing down to make it look nicer. Oops. Okay. Now I want to measure the current. So I need another scope. Okay. So how do I find it? I can just copy and paste this one. So I'm just going to Control C, Control V. Okay. This one goes here. This one goes here. And I'm gonna run this one more time. If I look at this one, so this is like showing two signals, current before and after. What do you think they should be? It should be the same, right? So let's actually see if this is the same or not. It is exactly the same. So the current before and after are the same because the current that goes through here is the same current that goes through here. Okay. So the current doesn't change, the voltage changes though. Okay. So I don't need to measure two currents. I just need to measure one current, but I wanted to show you this. One thing that you see here, okay, I wanted to measure this current and connect it to this scope. I had to take a very long wire and go here. So there is one way of doing this a little bit neater and tidier using something called Tack. So I'm just gonna put Tag. There's a from tag and a go to tag. So I'm just gonna take a go to tag, put here, and a from tag, I'm gonna put it here. So instead of having this long wire, I can make it even smaller. So I'm just gonna maybe move this one here, or this one. So we call the signal A. You can change it to whatever you want. So I can actually change it to inverter current. But if you want to match these two, you have to give them the same name. So I'm going to call this one inverter C. Okay, and now if I run it again, I'll get exactly the same thing. Okay, so I wanted to show you that you can use tags here as well. What else? do we need to see here? So I talked about multiplexer, demultiplexer. So let's just see if we can see everything on one scope. Okay, so here, let me just delete this one, delete this one, delete this one. Okay, so I have 1, 2, 3, 4, 5 and 6 signals I want to see here. So I'm just gonna make this one taking 6 inputs. 2 is what we used to have before, and I want to show you how to do the rest of them. Or let's just keep this one 1. Okay, so now what I need is basically something that converts 6 different signals into one signal. So what I do here is I add, again, I go to here, do mux, okay, demux basically, or like mux in this case, sorry. Put it here. As soon as I put it, it says like how many inputs, so I can actually write it here right now. So 6 inputs. Okay, so one of them is this one. Let's make it a little bit bigger so that it's clear. One of them is this one. 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 And over here, there are 2 signals here. I want to make them 2 separate signals. So what do I need? A demultiplexer. So one goes here, one goes here. So if I run it one more time, see everything here. So let's actually make it 6 separate things. Oops. Because I did it this way, it shows everything on top of each other. So it shows all the things on top of each other. So one thing you can do, can go to here, tools, or actually view, can add a legend. So here it actually shows which one is which one is the first one, which one is the second one, third one, fourth one, and so on. Okay, so if I want to actually see everything separately, I need to make this one with 6 inputs. So just want to show you like the examples of multiplexer, demultiplexer, what they are and what they do, because they're helpful things. But once we have 6 inputs, we can show them separately. So if I go here now, I should be able to, should be able to show them separately, right? So, okay, now this is the part that here I see like something that's very close to 0. Is it really 0? Okay, so over here you have something that you can fit to window. You have 3 options: fit vertically, horizontally, or both. Let me just do both. Now you see that it wasn't actually 0. It would go from 0 to 1, and this one go from 1 to 0. and the same thing here. Or you could actually do only vertically. So let's say like I want to focus only on this part. I want to see how much the ripples are. Okay. And over here I can go and fit it vertically. Okay, and I can measure the ripples. So that's another thing I wanted to show you. Now, one thing that Chris found, and it's very helpful, is that once you go here in the new version of MATLAB, it actually gives you the option to do the measurement without the need for ammeter and voltmeter, ammeter and voltmeter. So let's say over here I go and say do both branch and voltage measurement. Okay, so this would measure actually the voltage across the load and the current, the voltage across the filter and the current that goes through the filter. So let's actually click on this, can do apply and then okay. Okay, now what also, like, you can scroll, make it bigger, smaller, or you can hold it and move it up and down. So what we did here, basically created a tag that can be used to measure branch voltage and current of this RLC branch. So in this case, to actually show it on the scope, we need to have something called multimeter. Okay, so I'm just gonna drag and drop it here again. So right now it shows that it's measuring 0 things. Okay, let's double click on it. Okay, now it actually shows that, oh, there are 2 things that you wanted to measure. They're over here. Did you want to measure them? Yes, I want to measure them. So I'm just gonna move them here and I'm gonna update and close. Now you see like it shows 2. So now if I have another scope here, let's make this one 2 inputs. And let's add, oops, let's add a demux here. Okay, so now if I run this again, let me fit the window. If I run this again, I see the voltage and the current of that branch. Okay, so can you guys tell me what this yellow voltage is? Yeah, so the voltage is this voltage minus this voltage. Okay, so it's the voltage across the filter, right? So again, if I want over here, I can show them separately. Now, so this is basically what you need to do. You can also play with this inductance and see what's the impact of it. Let's actually make this 100 times smaller. And let's look at the current. See, now it's so bad, right? Also seems to have some sort of resonance here. But let's also make this one again back to 400. Let's see what happens if our load is inductive instead of capacitive. and run it one more time. So it seems that the ripples are even smaller now compared to the case that we had before. The ripples are smaller, right? Because now you know that the inductor is against the change of the current, so it makes ripples smaller. If I go back to what it was before, it should be fine. Now this is like, let's make it one phase. Now there is another way of doing single phase by having two bridges. Okay, so that makes it a full wave inverter or a full bridge inverter. If that's the case, over here we have to say single phase full bridge. We have two options, bipolar or unipolar. Let's just make unipolar. Okay, I click OK, and if I run this one more time, you can see the impact of it. You can see, for example, now let's take a look at our PWM signals. Our PWM signals are now different. When you have full wave bridge, you have 4 transistors. You have 2 arms. Each one would have 2 transistors. So now this line would actually have 4 signals, like 4 PWM signals triggering or firing the 4 switches inside here. If you have only one leg, you only have 2 switches. That's why we had 2 signals before. Now you're 2 levels, so sorry, 2 leg, so you have 4 switches, right? So this is like how you can do it. You don't need to make any changes here. You can also make the modulation a single phase bipolar modulation. So that's actually gonna be a different kind of PWM signal. Again, you can see here. So it's gonna be different. So all of this are stuff that I want you to play around and capture the waveforms. I forgot to mention about the display. This display shows the changes of the voltage online, right, in real time. So let's actually make this one very long. It's 1 second. If I make this 1 second, you see that it's going to take a long time for this to run, and it shows the changes real time. Okay, so that's basically what I asked you to do for the lab 0, to get familiar with MATLAB. Oh, I also forgot to mention that when you have two leg inverter, now you have 2 ports. So you can also make this one grounded, or you can actually connect it back to your to your load. So this one can come back here, or you can make both of them grounded. So this should be okay. It takes a long time because I chose 1 second. Okay, so yeah, and when you have your 1 second, then you see that like this is not very visible. Let me just make this one. Yeah, it's still not very visible. You can use a magnifier to zoom in or zoom out. Okay. You can also right click on it and zoom in, zoom out. You can also, if you go to view configuration properties, this one give you a chance to display or change Y limits, maximum, minimum, and add a Y label. So let's say like I want to add a label here to know that what actually this one is. Right now I don't know what it is. I just know that this is the first thing that goes to the scope. So you can add a Y label here, or if I go here, if I choose this one, sorry, and go to here, view, configuration, display, I can add a Y label here, or I can add a time label here, time unit here. So these are the things that I want you to play around with, to play with, sorry, and just like convert the built-in three-phase inverter example of MATLAB to a single phase. I hope this is helpful. If you have any questions, I'll answer that during the lab. Thank you so much.